Bonjour. This is the third video for the introduction to probability chapter, and today we will look at probability tree diagrams. So this is a tree diagram. You can see it here in the book. Here is a way of representing probabilities of different outcomes graphically in a drawing, and that makes it easier for us to understand. For simpler cases, it's really not very useful, but as the cases become more and more complicated, if you have series of random events, for example, if you toss a coin 3 times or 4 times or 5,000 times, it might become simpler to use a probability tree diagram rather than just do calculations. So, it is a graphical representation of probabilities of outcomes. Now, what is outcomes? Outcomes is issue. In French, by the way, it's called arbre des issues. And remember the three terms we had learnt in the previous two videos. One is probability itself. What is probability? It is a numerical value to estimate the chance of something happening in the future. And then we had learned two more terms. One is issue. Issue is all possible results of a random event or random trial. And then we had learned the term event, événement. Issue is outcome in English, by the way. And then we had learned the third term, that was event or événement in French, which is a combination of outcomes. For example, when you have a wheel like this, a pinwheel which you rotate and it stops against this red pointer which doesn't rotate. So then you have how many outcomes? You have 1, 2, 2, 3, 4, 4. But the event could be described as positive outcomes, or it could be described as all outcomes that are greater than 2. We have done this in the last video. You have also done some problems. Okay. So, how is a probability tree diagram drawn? So, the simplest trial that we can have, random trial, is a toss of a coin, and this is the way you do it. So, how many different outcomes can you have when you toss a coin? You can have two outcomes, head and tail, heads and tails, and so you draw two branches of the tree. This is a sideways tree. So you draw two branches. Each line is a branch, and then below each branch you write the probability of that branch or that outcome taking place. So when you have two branches for tossing a coin, then you have H and T, two outcomes, and you have probability of 0.5 there and probability of 0.5 here. So this is a simple tree diagram. So let's take another case. We take a case of a pinwheel where we have A, B, C. Each sector or each slice of the pizza, if you can call it, has the same angle. So they're all equally likely to stop in front of the pointer when you spin it. So then in this case you have three branches and three outcomes, A, B and C, A, B and C, and each is as likely to happen as the other. So the probability is 1 out of 3, 1 out of 3, 1 out of 3. And here we note that all the probabilities across one branch, not across one branch, added across the branches add up to 1, because obviously here also we said 0.5, 0.5. The probability of all the outcomes taken together is always 1, because it is it is absolutely certain that either you'll get heads or tails. So you will not get a third outcome. There are only two outcomes, so both of these will add up to 1. So indeed here you could see straight away from here, if I say my event is what is the probability of not getting C, then the probability of not getting C is the same as probability of getting A or B, and that is 1/3 plus 1/3, that is 2/6. Sorry, 2/3, sorry. So here it means that the probability of getting C is 1/3, the probability of not getting C is this plus this, which is 2/3. Okay, right. Let's take another example. So now we have a similar pinwheel but with 4 sectors, each occupying an equal amount of space on the pinwheel. So, but here we have A, B, A and C. So here if we do the probability tree, it looks like this: 1/4 A, 1/4 B, 1/4 A, 1/4 C, because each one of these has a likelihood of stopping at the pointer of 1/4. And again, you see, when you add all of these up, you will get 1. 1/4 plus 1/4 plus 1/4 plus 1/4 will be 1. But here you see it's the same outcome here and here. So you can, and this is what the book will expect you to do, you can collapse these two into one, and you can redraw the probability tree. You can simplify it here as A, B and C, because you only have 3 outcomes, A, B and C, and the probability of getting A is 1/4 plus 1/4, that is half. Yeah, because you can see it visually also, A occupies half of the circle. So here you get half, B is still quarter and C is still quarter. If you add up half plus quarter, you will again get 1. Now this is called the weighted probability tree, if you want to be very correct, or in French it's mentioned here, arbre des issues pondérées. Pondéré means weighted. Weighted means multiplied by a number. So here it is multiplied, this quarter is multiplied by 2 because there are 2 of them. Anyway, that is just for the sake of completeness. You don't have to remember it. When you are asked to draw a probability tree, you should draw it like this, not like this. You can draw it in rough like that, but finally you have to draw it like this. Okay. So in all that we have covered so far in the video, there is not really much that is a probability tree is of much use to us, because we don't have to draw a probability tree to know about that. If we toss a coin, we'll get half the chance, 0.5 probability of heads and 0.5 probability of tails. If we have a pinwheel like this, we know that we'll have 1/3 probability of A, 1/3 of B and same 1/3 of C. And similarly here you can see straight away that A occupies half the circle, so that will be probability of 0.5, B will be 0.25, C will be 0.25. So in all of these 3 examples, the probability tree hasn't really helped us much. We could have done it, solved these problems or calculated these probabilities without using the probability tree. But we will now look at slightly increasingly more complex examples, and then you will see that it helps us. Sometimes the calculations alone will become complicated. If we draw a probability tree, it becomes a little easier to understand. Okay, so now we have here this example I had given you earlier. I'll have to zoom in. So there's a bag with 7 tokens inside, numbered 1, 2, 3, 4, 5, 6, 7. The bag is opaque, it's not transparent. So you put in your hand and you pull out 1 token, and all the tokens have the same size and feel, and weight. So you have a random chance of pulling out any one of these tokens. So if we draw the probability tree, you will get 1, 2, 3, 4, 5, 6, 7. These are the outcomes. These are the numbers on the token. And each one of them, the probability is 1/7. If you add all of these, of course, you will get 1. 1/7 into 7 will give you 7/7, which is 1. And now we can convert these into outcomes. So we can say sorry, into events, these outcomes into events. So even if I say E1 is satisfied when I get an outcome which is a multiple of 3, then probability of E1, so how many are multiples of 3? This one is a multiple of 3, this outcome, so I add 1/7, I wrote 1/7 there. 6 is also a multiple of 3, so I take that one's probability 1/7 and I write it there, and there are no other outcomes that are multiples of 3, so the probability of E1 is 1/7 plus 1/7, which is equal to 2/7. So this is the this is, of course, again here the probability tree is not helping too much, because all of this we could have done as you did. In fact, this is the very problem I'd given you in the previous video. You managed to solve it, all of you, without using a probability tree. But here we are seeing how a probability can be used. So we took E2, we defined event 2 as getting an outcome which is greater than or equal to 4, and so here we saw that we could get 4, 5, 6 or 7. These 4 outcomes would satisfy this event, and so we have 1/7 plus 1/7 plus 1/7 plus 1/7, which adds up to 4/7. I have not written the intermediate step, but that's a total, and that's a final probability. And the final question I'd asked you was E3 is an outcome, is defined by an outcome which is a pair number greater than or equal to 4. So in that case, again, you have only this outcome and this outcome which satisfy the event. That is, if you get 4 or if you get 6, so again you will get only 1/7 plus 1/7, which is again 2/7. So in this case, what we have done is we have defined events in terms of outcomes and then calculated the probability. But in the middle, we have also drawn the probability tree. So now let's take an example where it starts becoming more and more useful. So I have again the same opaque bag, that means not transparent, you can't see inside, and you have 7 tokens again, but you have 1, 2, 3, 3, 3 and 4 and 4. So now if we draw the probability tree, we need not draw all 7 branches, because even though there are 7 tokens inside, there are only 4 unique outcomes, 1, 2, 3 and 4. So we draw only 4 branches, 1, 2, 3 and 4. We can see that the probability of 1 is 1/7. We can see the probability of 2 is 1/7. We can see the probability of getting a 3 is 3/7, because there are 3 tokens out of a total of 7 tokens. So I get 3/7, and for 4 it is 2/7. So this is a probability tree, the weighted probability tree for this particular random experiment. And again, if you add up all these probabilities, they will add up to 1. You can see 1/7 plus 1/7 plus 3/7 plus 2/7 is equal to 7/7 is equal to 1. If I'm going too fast, you can slow me down when you're watching on YouTube, or you can even pause and rewind. I'm just reminding you, you know that, of course. So now suppose I defined an event saying number is greater or equal to 2. Then you have to take this, the probability of this. So what outcomes satisfy this event? The outcomes that satisfy this event are 2, 3 and 4. Because only 2, 3 and 4 satisfy this condition, that greater than or equal to 2. So you add up 1/7 plus 3/7 plus 2/7 and you get 6/7. Okay, so now here you see it's starting to become a little bit more useful. Okay, this particular problem could have been done in a simpler way. We could have just taken 1/7, because that is the only outcome that doesn't satisfy this event, and subtracted it from 1, because 1 is the total, it adds up to 1. All the probability of all the particular outcomes, possible outcomes, is 1. So we could have taken the complementary event of this, or in French, événement contraire. Here in the book, page 68, l'événement contraire d'un événement A. I've written it in English, complement. Et l'événement qui se réalise lorsque A ne se réalise pas. That is, when it is the opposite of A. And here it says, on le note A bar. So here I have written E1 bar is contraire or complementary of E1. So E1, here is E1 is number is greater than or equal to 2, and so the opposite of that is E1 is number less than 1, and since there is only one number less than 1, number less than 2, there's only one number less than 2, so we get P of E bar 1 is 1 over 7. So we could have done P over E bar 1 plus P over, no, not we could have done, this is just to a confirmation that the probability of event E1 plus the probability of event E1 bar will equal 1. 6 over 7 plus 1 over 7 is equal to 1. I had explained this in the previous video. I'm just showing it again. Okay. So now we come to where a tree diagram starts becoming really useful. So we can extend the tree diagram for multiple trials. What does this mean? This means that if I take two tosses of a coin, first I toss a coin and then I toss it again. Remember, in one of the previous videos I mentioned that I have tossed a coin 5 times. So here I am only tossing it 2 times. So how would I draw the probability diagram for this experiment where I toss a coin 2 times? So this is the way to do it. So here, this is a new phone, so the lens is right at the edge, and you can see my finger just comes over it very easily just when I'm holding it. So here on the left of my hand is a standard tree diagram for one toss of the coin. So when you do it, you have 0.5 probability of getting heads, you have 0.5 probability of getting tails. Now, when you get heads, you're tossing the coin again. So again you have a 0.5 probability of getting heads and 0.5 probability of getting tails. And when you got tails, again you toss the coin, so you had a 0.5 probability of getting heads and a 0.5 probability of getting tails. So if you got heads and then again heads, I'm writing it here, head, head. If you got head and then you got tails, I'm writing head, tail. And here if you first got tail and then you got head, I wrote tail, head. And when you got tail and tail, I wrote tail, tail. Actually in English you use plurals, heads and tails, but anyway I've written as singular. So now the important thing here is that you multiply. So the probability is half here and then the probability is half here. Then the probability of in this experiment of getting tail and tail is 0.5 into 0.5, which is equal to 0.25. Similarly here, head and head, 0.5 into 0.25. Why 0.5 into 0.5? This is this number 0.5 and that number 0.5, you get 0.25. Similarly, if you go along these branches, then you get head and tail. First you get a head, then you get a tail, and again you get 0.5 into 0.5, 0.25. And similarly for this combination. Again, when you add all of these up, you will get 1. This is true for everything. So here we got 0.5, 0.5 added up to 1. you don't add it up here, because if you add it up here you will obviously get 2. 0.5 plus 0.5 plus 0.5 plus 0.5. No, at this point you have to calculate the probability of getting heads and heads, that is 0.2, here heads and tails 0.25 to 0.25, so all of that adds up to 1. You don't add, once you have a second level of trial, you don't add this up and expect it to get to equal 1. You do the multiplications first and then you add it up and then you will get 1. Okay, this is going to be a little long video, but we'll bear with it. So the important thing here to remember, and I can't emphasize this enough, I've written it in red there, we multiply probabilities along the branches. Okay, so let's take this particular example of 2 coin tosses and let's define events. So my event is, if I get both heads, then what is the probability of E1? The probability of E1 is 0.25, that is 0.25, both heads, 0.25. Simple. E2 is get at least one head. Now this is where the tree starts becoming really useful. So you have to see in all these combinations which of them there is at least one head. So this one there is one head. Okay, so this outcome, head and head, satisfies the event, so you add 0.25. Here again you have head and tail, this also satisfies it, so add 0.25. Here you have tail and head, again there is a one head, so you add it up and you get, and you add again 0.25, so you get probability of event 2 is 0.25 plus 0.25 plus 0.25, that is 0.75. Indeed, only in this particular case, tails and tails, is this event not satisfied. Okay, now event 3, we define it as get exactly one head. Event 2 was get at least one head, and event 3 is get exactly one head. So here, head and head, this outcome doesn't satisfy the condition because there are two heads. We wanted only one, exactly one head, but these two second, this one and this one, have exactly one head. This one has no head at all, so then you have to add this probability and this probability, so you'll get 0.25 plus 0.25 to get a final probability of getting exactly one head, 0.5. So about half the time when you toss a coin twice, about half the time you will get only one head. And of course, similarly for the tails also, because tails and heads are just 2 different sides of the same coin. Okay. Now if I have a 3 coin toss, so I have 0.5, 0.5, 0.5. So if I get 3 heads, it will be 0.5, 0.5, 0.5. That will be 0.5 into 0.5 into 0.5 is 0.125. You can do this on your own. Half into half into half is 1/8, which is 0.25. And similarly, so now here you have 8 different outcomes. I have not written HHH and HHT and HTH and so THH and THT and TTH and TTT. I have not written that here, but this is what it means. So again, if you add all of these up, you will get 1. 0.125 into 8 is actually equal to 1. So now if I ask, what if my event is defined as 3 heads, what is the probability of that? So you see there's only one head, one head, one head. There's only one branch, one sequence of branches that leads to this, that satisfies this event, and I get 0.125. So the probability of getting 3 heads consecutively on, if you toss the coin 3 times, is 0.125. Okay. So if I say getting at least 2 heads, now this is slightly trickier, and this is where the probability tree comes in very useful. So 2 heads, so the first condition satisfies it, the first branch sequence of branches, because you've got 3 heads there, which means at least 2 heads. So you will see that getting at least 2 heads, this satisfies it, this also satisfies it. I'll use a pen because my finger is too fat. So this satisfies it because you have head, head, head. This satisfies it because you have head, head, tails, again 2 heads. This satisfies it because you have head, tail, head, 2 heads. This branch doesn't satisfy because it is head, tails, tail. And here THH also satisfies, but the others THT and TTH and TTT don't satisfy. So you will get only 4 cases where 4 outcomes where you get at least 2 heads. So that means 0.125, 0.125, 0.125, 0.125. Actually, if I went back up here and just underline them, see this one you get 2 heads, this one you get 2 heads, this one you get 2 heads, this one you don't get 2 heads, and this one you get 2 heads. So you have 4 of these, 4 outcomes where you've got 2 heads. So I've added up 0.12, 0.125, 0.125, 0.125 4 times to get half. So if you toss a coin 3 times, the probability of getting at least 2 heads is 0.5. Which now leads us to today's in-video problems, which is E3 is getting exactly 2 heads. Here it was getting at least 2 heads. Here E3 is getting exactly 2 heads. So what is the probability of getting E3? You have to calculate and you have to send me the answer. And E4 getting exactly 1 tail. If your E4 is defined as the outcomes that give you exactly 1 tail, then what is the probability of that happening? So now this is where I will stop. We have already gone 28 minutes, and the next thing we will continue. I thought I would do that now, but we are already out of time. It's too long. So I will stop here, and in the next video we will again look at a few other aspects of the probability tree. Okay, I stop here.